Okay, welcome back everyone. So in this video we're going to be talking about a pretty special case of Newton's second law. This is what we call equilibrium. And basically this is when an object is not accelerating. So there's different types of equilibrium. We're not going to talk about when things rotate right now because that gets a little bit crazy. But for the most part, equilibrium is an object is not accelerating. So we know that F net is equal to 0. And so this actually has two different ways that this can happen, which are basically the same thing. But if F net equals 0, the net force, then automatically we know acceleration is equal to 0. And that tells us a lot of things. It says that the net force in the x direction has to be equal to 0, the net force in the y direction has to be 0, and if we had more directions like z or whatever, that would also be equal to 0. But it also tells us that there's kind of two ways that this can happen. One is if the speed of an object is constant, and the other is if the speed of an object is 0. Now, option number 2 is the one that most people think of when we say something is in equilibrium. Oh, they think of something just sitting at rest on a table. And that's kind of dangerous because equilibrium just means that the object is not accelerating. It can still be moving. For example, if you have a car which is moving down the highway, it's got cruise control, it's got a speed of, let's say, 65 miles per hour, and can you say that there's no forces acting on the car? Well, as a matter of fact, there's lots of forces. There's a force of gravity, there's going to be a normal force, there's going to be some sort of push from the wheels, some sort of driving force, and there's going to be friction between the tires and the road. And all of those forces are acting, but yet the car is still in equilibrium because the acceleration is 0. And this is a very important conceptual thing to think about. So you want to make sure that you understand that an object can be moving and also be in equilibrium. So sometimes if something is not moving, we call it a static equilibrium. Okay, and we sort of did an example of this with the last one, but let's look at, this is on page 138, number 105. So we have an inclined plane and a 5-kilogram block placed on this plane, and it's adjustable, so we can change the angle. What angle of the incline would cause the block to start sliding down the plane? Okay, so we want to know basically what's the angle where we're just barely leaving static equilibrium. Okay, so what we need to do is look at the fact that both of the objects are wood, and we know that the static coefficient of friction is 0.58. So I just looked this up in a table in the chapter. And as we've seen before, forces on an inclined plane, you have gravity, you have normal force, and you're going to have friction. And force of gravity has Fg perpendicular and Fg parallel, and the two forces we want to make equal are Fg parallel and friction, static friction. So mg sine theta is equal to mu F normal, and we've already said a few times that on inclined planes that's often, but not always, equal to mg cosine of theta. Sorry, I got a bit ahead of myself. We don't know the angle. So this is theta and this is theta. Okay, and this comes from the fact, let's back up the train a little bit, that the net force parallel is 0. So that means that if upwards is positive, then we have friction minus Fg parallel is equal to 0, or Fg parallel is equal to the force of friction. So that's where all of this comes from, because we have static equilibrium. And then we can cancel things out, and doing a little bit of math, we figure out that the tangent of theta is 0.58, or theta itself is about 30 degrees. And so that's really all that there is to static equilibrium.